I've started recording the lecture now, and what I'm going to do now is walk you through the material in chapter one of the book that I'm writing. So I've released chapter one on the Moodle webpage. So let me share my, let's see, how do I do this? All right. You should be seeing my email right now, and now you should be seeing my Moodle page. Is that correct?
That's
Yeah.
correct. Yes.
Yes.
Yeah,
Yes.
so on the Moodle page, what you will see is under lecture 5, I've just uploaded, I re-uploaded a version of the chapter 1 notes, right? So you can download this PDF and read it, okay? So that's part of your homework. Part of your homework is to, oh, there's somebody coming in, just a minute. The homework assignment for this week will be to read this chapter carefully and perhaps listen to my lecture one more time that I'm recording right now, and to do the homework. The homework will be all the exercises at the end of this chapter. Okay, that's your homework. Has to be submitted next week. I would prefer to have it all in R Markdown, but if you're unable to use R Markdown, you can just put them into a Word file, make a PDF out of it, and submit that. Okay. All right.
Excuse me?
Yes, please.
There are still people waiting in the waiting room, I think.
I know. Yeah. The problem is that I'm trying to concentrate on giving the lecture. I do see these messages that there are people coming in. This is very distracting for me. I'm very unhappy about this. But it seems
Pralan,
that I
if you
don't know
want,
what.
make me a co.
I'll make you
What
a
do we call it?
co-host and you deal with it, okay? Because
Exactly.
it's very distracting for me to try to give a lecture and at the same time keep tracking all this stuff. You're a co-host now. You can. Um, Now you're a co-host, right?
Fine. Thanks.
Thanks. Yeah. Yeah, it is a very difficult aspect of Zoom right now that people keep walking in late. They don't really walk in late into a physical class that much. That happens much more rarely, but people are more casual about coming into Zoom lectures, I think. They don't take it as seriously, I
A
guess.
problem with connection because I tried to connect to since 10:08 and only now I
Yeah.
yeah. So
Yeah, I think that it's not just like a different behavior, but there's also the internet problems that we are having, right? So I understand that there's many different reasons for coming in late, and in any case, we are in this Corona crisis situation, and I mean, my own life is completely turned upside down right now. So I'm doing two jobs at the moment. One job is my current job as a professor, and I'm also teaching my son physics, chemistry, and mathematics because he's sitting at home and he's doing homeschooling, and I'm going completely bananas right now. Like, I'm trying to study class 9 chemistry. I have no idea. It's all in German. So like half the time, like I'm just Googling the words to figure out what they even mean. So like it's a serious challenge that for all of us. I think you probably are also facing such problems. So these are bizarre times. Okay, so where was I? Let me see. So what I want to do now is I did share my screen. Where is it? Where's my shared screen? Here it is, right? Okay. So you guys should be able to see my Chrome screen now. Sorry, my not really good at this. Yeah, you should be able to see my OneNote from Windows. Yes. And then
Yes.
I'm also going to pull up my PDF so that we can start working through it. Let's see. Um, Sorry, guys, I'm not really good at this. Here we go. All right. Okay, so we are looking at the opening page of my upcoming textbook, which we are working on right now. And as you can see, this book is going to be about 200 pages, is currently about 200 pages, but it's going to be much bigger in the end, right? So today we are going to look at this chapter, Foundational Ideas. This chapter is actually very, very important for anything that you will do with statistics in all your life. Every year when I teach this course, I teach this foundational chapter, and many people get irritated with me, right? So people get annoyed with me, and I often get complaints in the teaching evaluation afterwards that why did you bother us with all this technical nonsense? All this mathematical nonsense. Why are you teaching us all this? So let me say a few words about why I wrote this chapter the way I wrote it. Okay? When statistics is taught in psychology or linguistics and areas like this, the non-statistical areas, when it's taught to lay people, the teachers try to dumb it down. They try to simplify the story so that it becomes more practical and more accessible. But when they dumb it down to simplify the story, the important details are thrown away. Okay. So students become professors and they become world leaders in psychology and linguistics without having any idea about the underlying foundational concepts. And what that does is it's like a domino effect. If you don't have the first ideas clear in your mind, everything else breaks down after that. And so you will have the situation that you will have big shot professors in MIT and Stanford and so on who have literally no idea what they're doing. They're 30, 40 years into their careers. They're publishing 300, 400 papers. But if you ask them, what is the p value? What does the p value tell you? They cannot tell you anything. And the reason is, so the problem is that they go that far into their career, they become very successful. At that stage, being a full professor in an Ivy League university, it's very hard to tell yourself that, hey, I actually don't understand this stuff. You can't go back anymore, right? It's too late, right? So, what I'm trying to do in my lectures is I'm trying to give you these deep foundational ideas and I'm trying to make them as easy as possible. Okay, so I'm trying to bridge the gap between what the mathematicians and statisticians would do in a stats lecture and what we need in practical settings. I'm trying to bridge that gap. The price we have to pay is a little bit of mathematics, not even calculus, but maybe a little bit of, I have to show you a few calculus things. The price that we have to pay is having to face a little bit of formalism, okay? But I want to assure you that I'm not doing it to torture you. I'm doing this because I know what will happen to you 10 years down the road. You will only understand the importance of this chapter after you have engaged with data for many years. You won't understand it right now. So right now, what I want you to do is to trust me. Okay, I've been in this game for 20 years. Trust me and try to understand these concepts for what they are. Don't question yourself on why do I need all this right now, right? So this is a long journey. Statistics is a lifelong journey. I'm preparing you for the future, okay? So you have to trust me and listen to what I have to say here, okay? So don't ask yourself, why am I doing this? That answer will come to you in the end. Okay, so those of my students who actually understood this chapter, they have come back to me, some years later and told me that this was the most important thing that they ever learned in their life. And why didn't they ever learn it anywhere else, right? So it takes time to digest this stuff. So this is your first contact with these ideas, but I will try my best to make them easy to access. Okay, so that's my preamble now. I'm trying to preempt all your complaints about this. Okay, all right.
Sorry, can I just add something?
Yes, you
Some
can.
comment?
Please go ahead.
Yeah, I'm a guest here. I look for Professor Vasist about statistics. I have a doctorate now, but in 2018 I got my doctorate in linguistics. So I work on theory, gather data, and the advice for me was like, oh, okay, just do this test, and now I'll allow you to check the p-value, and let's see what's happening. And then, okay, oh, p-value is significant. I was so worried about the theory that I didn't have time to work on the
Yep.
statistics. And here in linguistics, we don't have any classes, specific classes on statistics. So I was just looking for p-values, and I had no idea what are p-values. I had my doctorate, as most of people do,
Yes.
especially in Brazil, and you have now so much advanced. I was worried about gathering data, going to schools, work with kids. And then, okay, I looked for p-value, and then I started asking myself, after the thesis was done, I had my defense, and then I said, what does it mean to be significant? Significant of what? What is the p-value? And then I started asking myself. And then I decided to go back, and then I understood, okay, I have to go back to mathematics. I have no basis at all. So it's very, very annoying to do stuff in the dark. And then you
Mhm.
have to look for stuff that you have no idea what you're doing.
Yes.
And still you get your doctorate. And it's what you said. Soon I will be teaching. And then what? I will teach my students, okay, look for the p-value. That's not the correct attitude. So, and then I have colleagues with attitudes like, oh, I prefer just a literature or something like this or language. I don't care about mathematics. So this attitude is very common.
Yes.
And I mean, working with experimental stuff, you have to deal with numbers. That's essential. So that's just for me to ask. I mean, you may ask yourselves now, why are we learning this? But I mean, this is extremely important. At least I
Yeah.
think so. Sorry, just a
Yeah.
comment.
Yes, thank you. That's exactly what I'm trying to get across. So you're further down the road and you have felt the pain, that these people have not felt yet. So most of you are just starting out in your lives and you have not actually hit the wall yet, right? I'm trying to save you from giving you the seatbelt, that will prevent you from crashing and burning when you hit the wall, right? So, I mean, I know that many people in linguistics come to linguistics thinking that it's a kind of philology, it's like the old style philology that we used to do. And but linguistics is no longer more philological, it's more like a natural science now. And so you have to be prepared to do mathematics no matter what you think anymore about linguistics. So it's not just in the statistical side. If you're a theoretician in semantics, for example, you're going to be doing the lambda calculus. You're going to be doing proof theory, which is pure mathematics. Okay, that's proof theory. These are the Polish logicians, So we'll be studying that kind of stuff in semantics. And there are in other areas there will be programming skills are needed, and so it's just pure hard science now. Okay, that's why we give BSc and MSc degrees in linguistics. We don't call them BA and MA anymore. Okay, so there's an expectation that you enumerate, and so if you're afraid of numbers, you should get over it and just um, make numbers your friend. Okay, so anyway, so let me get started now. So the important ideas I want to get across, and I might take more than one lecture for this if I need to. The important ideas I want to get across in this foundations lecture is what is a distribution and what can you do with a distribution? Okay, so in the quizzes that I gave you, the two quizzes that I gave you, I showed you some reading time data, right? And so it was, if you remember, in the reading time data, we plotted some things like box plots, if you remember. I don't know if I plotted the box plots or not, but you must have seen things like this. You can have the median value of the data that you have as a vector. You have a vector of reading times, right? And you might have, so this is called a box plot, right? This box plot is summarizing all the data points. It's giving you the median value, the top and bottom quantiles, so the 75th and 25th quintile, and any extreme values might be showing up here. That's one form of data summary that you must have seen graphically. Another form would be just to draw So just draw the probability distribution of the data. So, so what this distribution is showing us, this one here, what this is showing us on the y-axis, it is showing us the, well, I don't know what it's showing us here. I will explain that later. But on the x-axis, I'm seeing different values, right? Different possible values of the reading times. And intuitively, what we are seeing is that the most frequently occurring values are within this range. How do I know that? Because of this higher height of the of this curve here. This part of the curve has fewer values on the x-axis. That's why it's coming down closer to the 0 point here, okay? So that's what these distributions actually show. So if I show you a distribution of heights, for example, the heights of students in Potsdam, right? So there will be some height which will around which, so this range will be the most frequent height on the x-axis. The x-axis contains the heights. Okay, it's that real number line that contains the values that we are interested in characterizing. And this range, for example, contains the most frequent values. And I know that because of the big height here. These are, so there are very few short people, right? And there are very few really tall people. That's how I know. It's from that height of this curve, okay? So that's the intuition behind a probability distribution, okay? So let me formalize this now a little bit. So what we're going to do is we are going to start by talking about, let me just go through this. Right. So we're going to start by talking about a very practical situation. Let me take this case here, right? Let's look at this practical case here, right? We are talking about what you're seeing here in the output here. What I'm doing is I'm repeatedly tossing a coin 10 times. I toss a coin 10 times and count the number of heads each time. And I do that again and again. So the first time I got 7 heads, the second time I got 7 heads again. The next time I got 4 heads, then I got 7 and 6, then 5 and 6 and so on, right? So these are different numbers of heads that I'm getting when I'm tossing a coin 10 times. This kind of distribution is called a discrete distribution. More specifically, what we are doing here is that we are thinking about some black box. There's some black box out there. This black box is generating data, is generating these numbers, okay? And so the thing I want you to understand and to put in your mind is that what is this black box? This black box is a generating process. It's a generative process, okay? And this generative process has a name. The name of the generative process is that it's called a random variable. It's called a random variable. So what I want you to do is I want you to meditate for a few minutes on what the underlying data structure is for this random variable. It's an object, it's a black box, it's got some machinery inside it. And we're going to now open the black box and look at that machinery, okay? So what is this machinery? The random variable, the idea of a random variable. So the first thing we have to think about is that we will want to give every random variable a name. Just like you have a name that uniquely identifies you, I need to talk about each random variable with a name. I could use any name, but I'm going to use Y. Okay, I'm going to talk about a random variable Y. And what a random variable is going to be is that it's going to be a function. Do you guys know what a function is? Does anyone know what a function is? So here's an example of a function, okay? 1 plus 1 gives you 2, right? This plus sign is a function. It maps certain numbers onto other numbers. Here's another function, okay? X squared. You give me a number x, I will square it and return the square of that number, right? So for example, if the numbers that I'm thinking about are 1, 2, 3, and 4, x squared is going to be what? 1, 4, 9, and 16, right? So what's happening is that I'm mapping each number to a particular value. That's what a function is. One important property of a function is that the this part here that I'm mapping from, we'll call it a domain, right? This is called a domain. And this thing is called the range or the codomain, the different names in mathematics. Have you guys all seen this in school? You remember this? Okay. This is not news, right? So one important property of a function is that a member of a domain cannot map to more than one element. It has to uniquely map to one thing. Otherwise, it's not a function. It becomes a relation if it's mapping to more than one thing. So there's a unique thing that you map onto in the codomain. And that's the definition of a function. So the random variable is a function. Oops, Daisy, what did I do? Okay, so the random variable y is a function that maps all the possible events that can happen. Okay, I'll call those events S. It maps them onto the real number system. You guys know what the real number system is? Everything going from minus infinity to plus infinity, right? All numbers in between those two things. Yeah. So the random variable is actually a function that maps all the possible events, right, to a real number system. So let's look at some examples, okay? I toss a coin 10 times. What are the possible events that I can have? I've tossed a coin 10
A
times. I
heads
could
or
get a heads or
tails.
tails. Yes, go ahead. Sorry. Yes.
You can have either heads or tails as your result.
Yes, I've done it 10 times. Okay. So I'm going to have 10 outcomes, right? So one possible outcome could be, so n is equal to 10. I'm tossing the coin 10 times. So one possible outcome is that I get
10 heads or 10 tails.
10 heads or 10 tails, right? Right. I hope that's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, that's great. So that's 10 tails, right? I could also get one heads. I could get, if I get one heads, how many different ways can I get that one heads? I could get heads and then tails everywhere after that. I could get tails and then heads and then tails after that, right? So there are how many different ways of um, getting one heads in this situation?
10 different ways.
Thank you. Yes. So there's more than one way of getting that, right? But the upshot here is that I could get k equal to 0 heads, k equal to 1 heads, and all the way up to 10 heads. So there are 11 possible outcomes here. Okay. Notice that when I say I get one heads, I'm ignoring the order in which it appears. I don't care what order it appears in. There are 10 different versions possible, but each of them is one heads, right? Okay. So the function that represents this process of generating these heads, right? What will be the numbers that I'm mapping each one of these things onto? This is one possible event. All tails is one possible event, okay? I'm mapping that to a number. What's that number? 0. 0 heads, okay? What happens when I'm mapping one heads? What do I map that onto? That's to the number 1, right? So what's going on is I've got a bunch of possible events, and these are the events here that I'm talking about, right? And I'm mapping them to different numbers here. That's what that random variable is doing. It's you get to decide this, okay? Here's another example. Different situation. I will toss a coin till I get a heads. Okay? So now I'm not tossing the coin 10 times. It's not a fixed number anymore. Okay? So what are the events now? One possible event could be that the first coin toss gives me a heads. Okay? I'm now counting the number of times I have to toss the coin till I get a heads. That's the number I'm mapping to. Okay? So the event now is 1. Gets the value 1, right? If I toss the coin twice and I get the heads in the second hit, then it's 2, right? So the function depends on what the experiment is about and what your goal is here. Okay. Third example, reading times. Okay. So reading times. So this is a continuous measure. This is no longer coin tosses anymore, because between 100 milliseconds and 200 milliseconds, there's an infinity of possible numbers. Okay. Continuous value. So I've got a random variable here again, and I've got some events S. Those events will be what? S is the sample space, okay? That's why it's called S. Those events are the reading times that are possible. It's an infinity of values. It's an infinite set, okay? And this is being mapped onto the real number system. What number would I map 500 milliseconds, which I've observed? That's an observed value. It's in my sample space. What number would I map it onto in this function? The number 500. The number on the right-hand side, that's in the real number space. This is an observed value from the experiment. Okay, so similarly, same situation, EEG data, right? So this was in milliseconds, right? EEG data is in microvolts, right? Microvolts. What would happen here again? Here I've got some sample space, that's our measurements in the from the machine, and we are going to be mapping each of the observed numbers to the real number space, and it'll be the same number that we observe. If you observe a 5 here, we have 5 here, right? So depending on the situation, we've got what we have in the abstract case is that we've got a random variable and there's some sample space. It could be discrete, it could be continuous, and it's being mapped onto a real number system. Now, the numbers that we map onto, right? For example, in the coin toss example that I'm working with, right? I've got 10 coin tosses that I'm doing, and the possible outcomes are 0 heads, 1 heads, and all the way up to 10 heads, right? There is the numbers that are mapping the function is mapping onto. That set of numbers is called the support of the random variable y, right? So this is the set 0, 1 to 10. It's called the support of y. These are all the possible numbers we can map onto, okay? So what's the practical implication of talking about the support of y? When we're talking about reading times, for example, okay? Suppose we are modeling reading times. The support of the random variable representing the reading times is bounded at the left edge by 0. It cannot be less than 0. You cannot have reading times less than 0. So what we say is that the support of the random variable is bounded from below by 0. Okay? Are we good? That's how I'm going to talk about the possible values that we are mapping onto. That will be called the support of y. Okay? All right. So what's important about a random variable is that every element in the support of y, okay, so every element in the support of y, so I'll call the element y. I could have called it anything else. I could have called it k or whatever, right? So every element y in the support of y has some probability associated with it. For example, in this case, when I'm tossing the coin 10 times, there's a certain probability of getting 0 heads, of 1 heads, of 2 heads, and all the way up to 10 heads, right? So what we will do is we will write this formally and say that the probability of y, right, is going to be defined by something called a probability mass function. I'm talking about the specific case of a discrete situation like this coin toss case. I'm talking about this situation only right now, okay? So this thing, every possible outcome in the support of this random variable will have some probability associated with it. And how will I define this function? Notice that this is also a function, okay? So how do I define this probability function, this probability mass function? There's actually a mathematical form that I can write down for this probability mass function, okay? So this probability mass function is going to be written like this. N choose k, theta k, 1 minus theta, n minus k, okay? So what are all these things here? What is n choose k? Do you guys know what this is? This is basically something that you will encounter in combinatorics. And what it's telling you is how many ways you can choose k things out of 10 things. Remember when we looked at the one heads, there were 10 different ways in which we could get one heads, right? So when we say 10 choose one, we are asking how many ways are there that you can get a single head out of 10 coin tosses, okay? So that's what that term does. And this term here has a probability value theta, which tells you the probability of getting a heads. That's a number between 0 and 1. And this formula is going to determine the probability of getting 0 heads, 1 heads, 2 heads, or 10 heads, or so on. If you plug in the numbers n and k and theta into this function, it's going to give you the probability of observing that number of heads. That's what the job is of this probability mass function, okay? All right, so let me show you what this probability mass function looks like in the case of this particular example that we are studying right now, okay? Right, so this is what a probability mass function is going to look like. So the first example that I'm showing you here is the probability mass function for 10 coin tosses, where the theta that I just showed you earlier, remember what the theta was? It was n, the whole function was n choose k, theta k, 1 minus theta, n minus k. So what I've done is I've put n equal to 10, and these here are the possible k's, 0 to 10. All the possible k's, okay? And on the y-axis, I have the probability, which I compute using this function, okay? By plugging in the value 0.5 into the theta, right? That's what this is, right? And so what you're seeing is that the most likely value is 0.5. I see that here. See that? 0.5 is the most likely value. And all the others go down smoothly, low down. If I change theta to 0.1, right, here in this function, if I change theta to 0.1, what changes? What has changed now? Any ideas? The shape has changed. What's the maximum point?
The maximum point is at 1 now.
I set 1 now. The maximum point it is 1 now. If I change theta to 0.9, the shape changes again, and the maximum point is at 9. Do you see the pattern? I have 10 coin tosses. 5 out of 10 is 0.5. That's the maximum point when theta is 0.5. 1 out of 10 is 0.1, and that's the maximum point when I have, so 1 is the maximum point when I have theta equal to 0.1, and 9 out of 10 is the maximum point here, right? And so that's why this point gives you the maximum here. So the theta parameter is actually controlling what the maximum point is going to be in this function. That's the big insight, okay? All right. Okay, so this is the way that we will write the probability mass function from now on, right? This function has a name, it's called a binomial distribution. And what we are going to do is we're going to write, instead of writing P of Y like I did earlier, in the binomial case, I'm going to write K, vertical bar, and theta. Why do I write it like this? Because K is the data that we will get. It will be a random outcome from the experiment. It will differ each time that we do the experiment, right? We saw that earlier. See that? I get different Ks each time I run this simulated experiment, right? And n and theta are given values, right? We have to decide what numbers to give to theta and what sample size to have. So those are given. And that's what that vertical bar is doing. It means given n theta, what is the distribution of k? Okay, that's what this function is doing. Okay, so
Sorry, can I ask a question, please?
yes.
I'm wondering if theta refers to the probability of success. How do we determine it in advance?
Yes. How do we determine the probability of success, right? So what we can do is when we do an experiment, right? Let's say I do the experiment, n equal to 10, okay? Sorry, n equal to 10. And suppose I get k equal to 6 successes. So how do I decide what theta is going to be now? I've just observed this. I've just observed, I don't know what theta is, right? How do I decide what theta might be? Hajira, what do you think? What should I do?
Well,
this is all I have.
Yeah, but then I guess that's your success because you observed it 6 times. So
I observed 6 successes, yeah. So how can I proceed? Can I make a guess about theta now based on this information?
I guess that could be your number. Yeah,
Yes,
sorry,
yes.
I'm very naive when it comes to this.
No, you're going in the right direction. I don't think I think you're just you're going exactly in the right direction. Go ahead.
Well, 6 out of 10 could be your, yeah, theta.
Exactly. 6 out of 10 is going to be our estimate of theta. We're going to say that this is an estimate of theta. Remember that in real life, we will never know what theta is. We're going to estimate it from the data. Once we have this information, we're going to figure out an estimate of theta. We're going to write that estimate as theta hat. Why? Because it's not the true value of theta. You have to make a distinction between the true value of theta, which is called theta. We don't know it. And our estimate of that. Okay. So you did exactly the right thing. You used the data to figure out an estimate of theta, and that's exactly how we will proceed. Okay. So what we're going to do is we are going to do an experiment, calculate the number of successes, figure out the number of successes, and use that to calculate an estimate of theta called theta hat. Okay. So that estimate of theta is going to be called something like this. It's going to be called the maximum likelihood estimate. And the question is why? Now I'm going to explain that. Why it's called the maximum likelihood estimate, okay? First of all, to understand what it means to be a maximum likelihood estimate, you have to understand what a likelihood is, okay? So what's a likelihood? The likelihood related to the binomial, to this random variable that we are discussing right now, is exactly the probability mass function that I have just shown you. With the difference that the probability mass function is treated as a function of theta. So what we have done so far is we've done the experiment. Our sample size was 10, let's say, and let's say we got 6 successes, okay? That's it. Experiment is done. Right? This is a fixed result that we have now. This is never going to change now. That's the result we have. So if in the probability mass function, if I plug in these numbers, sorry, I've got 7 here. So let me change that. 7, okay? If I plug in the numbers 10 and 7, right? The only variable left now is the variable theta. So I can rewrite this function as a function of theta, right? And you can see this on the right-hand side. In the right-hand side, I've put in all the numbers. N and K are in there. They're constants now, okay? This will just give me one numerical value, 10 choose 7. But this part of this equation actually depends on theta now. So if I plug in different values of theta from 0 to 1, I can plug in any value between 0 and 1, and I will get some number. That's the result of that function. And I can plot that function, okay? So let's plot it and see what happens. For the situation that I'm discussing right now, where n is equal to 10 and k is equal to 7, what you're looking at right now is the maximum, is the likelihood function. What I've done is I've taken the binomial function, which I just write as bi, as a function of theta alone. So I'm putting in different values of theta here. Okay, different values of theta here, and I'm plotting this line. For each value of theta, I'm plotting the line using this function that I just computed, okay? So I'm getting the likelihood function here. And what do we notice? What's the maximum value in this function? The maximum value in this function is centered at 0.7. And Hajira, that's the reason that we use 7 over 10 as our estimate of theta. That's the reason why we use 7 over 10. And the reason is that this 0.7 estimate, okay, this is 0.7, is going to tell us what the maximum point in the likelihood function is, given the data that we have. The data are fixed, okay? So once you know the data, you know what the maximum point of the likelihood function is by computing this using this formula. Are we good? And because it's a maximum point, right? This is the highest point in this curve. We call it the maximum likelihood estimate, MLE. Very important idea.
Makes sense. Thank you.
Okay. So there's a deep reason why we use the number of successes divided by 10. It's not just a guess. There's actually a deep mathematical reason for this, right? All right. Okay. There's one little warning I have to give you though. Even though in your one experiment, you got 7 successes out of 10, and your maximum likelihood estimate is 7 out of 10, so 0.7, that does not mean that the true, oops, that does not mean, wow, that the, what have I done here? Does not mean that the true value of the theta parameter is 0.7. That does not entail that. Why? Suppose I toss the coin 10 times, I could end up with 10 heads. It is possible. It is theoretically possible, and it can happen in real life. Okay. So let's see. Maybe I'm just making this up, or maybe we can demonstrate this point. Let's see if this works. Okay. Can you guys see my R Studio? Yeah.
Yes.
All right, so let's take a look at this, okay? So we're going to generate some random data. I'm going to show you later how to do this. But let me say that my n is 10, and my size is 1, and my probability is 0.5, okay? So the probability of success is 0.5 here. I set the probability, I set theta at 0.5, and I'm going to produce 10 outcomes, 10 coin tosses. So this time I got what, 3 heads, right? And I've got 1, 2, 3, 4, 5, 6 heads. I've got 1, 2, 3, 4, 5, 6 heads again. I can keep doing this. I want you to look at this here. I've got 8 heads here. 8 heads in a situation where the true probability of success is 0.5. Okay. So there's a very practical example of this. Like when you're studying aphasia, right? People with aphasia, there are people who work on aphasia, brain damage, right? People have brain damage. They can't actually comprehend sentences accurately. So what they say in aphasia research is that this patient is above chance and this patient is below chance in performance. And the way they do it is they will ask them 10 or 20 questions and calculate the proportion of successes. And if it's significantly above 50%, they will say, oh, this person is above chance. Okay. But look here, this could be an aphasic patient with 80% accuracy. What they would conclude is that this person is fine. They have no impairment. But the underlying parameter is 0.5. They're at chance. So the big insight for you guys is that the maximum likelihood estimate from a particular data set need not necessarily reflect the true value of theta. The data are what they are. They might be a very deviant sample, right? You don't know what the reality is. So don't ever be fooled by that, okay? People think that because maximum likelihood estimates are supposed to reflect the true value, every single data set will give you the true value. That's what people think, but that's not true. And this has dramatic consequences in science because you publish a paper, you think that, oh, I've got the maximum likelihood estimate. It must be the true value. You redo the experiment, you get a completely different number. Okay? Happens all the time. This is a very practical outcome. Okay, now what the maximum likelihood estimate actually means is that if you increase the sample size to infinity, you will approach the true value of theta. That result is guaranteed. This is called an asymptotic result. Asymptotic means if you keep pushing n to infinity, right, you reach a particular asymptote, you reach a particular stable point that gives you a stable value. That stable value will be the theta if you increase the sample size to infinity. But when do we have infinite data points? We never have infinite data points. So the reality of data analysis puts us in a very awkward situation, right? The theory we are working with relies on asymptotic results. These are theoretical claims about the true value of theta under a completely idealized situation. The reality is that we have limited data. Often we have ridiculously limited data, okay? And so our trust in the maximum likelihood estimate has to be very, very carefully calibrated. So there's a famous statistician, Andrew Gellman. He often says that maximum likelihood estimates are super duper biased, right? People are, in statistics, we say that the maximum likelihood estimates are unbiased estimates. But they're actually super duper biased if the sample size is not sufficient. So you have to understand this point by playing with it a little bit. I will give you more insight into this. I just wanted to introduce this idea though. Nevertheless, we now know what a maximum likelihood estimate is. It's a very important idea. So let's keep going. So let me get back to my, did I get thrown out? Oh shit, sorry. I got thrown out of my Windows session. I have to restart the sharing. Sorry, just 1 second. Just one moment. I'm going to go nice and slow on this chapter. I might take a couple of lectures on this because it's really important to really digest every detail. So I'm not going to rush through this. Okay. So let's get back to my OneNote. Where is it? Yeah, right. And my PDF was here. Okay. So this is where we were, right? You guys can see my maximum likelihood estimate curve, right? Okay, good. All right. So now I want to talk about, now we know what a random variable is, okay? Just to remind you, we have a random variable y, which is going from some sample space to the real number system. And we have the support of y, right? And we have a probability mass function, which takes every possible element of the support of y and maps it onto some number between 0 and 1. It's a probability mass function, right? And the specific example we are working with here is the binomial distribution. Okay, so now the question is, what can I do with this distribution? So what we can do is the following. So let me just quickly draw the picture that I had drawn earlier. I had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 successes. And what I had done is that for theta equal to 0.5, I had drawn this probability mass function. It's not very nice. I'm sorry, I'm doing this by hand, but I do want to have control over it here. So you get the idea, right? So that's how it is. Okay, so this probability mass function that I've just drawn allows us to read off the probability of getting 5 heads, right? If I want to know the probability of getting 5 heads, let's say the probability that y is equal to 5, I just need to look up this function and look at the y value here, and that tells me the probability, right? There's a function in R that computes this value for you. That function is called d binom. Okay, I will explain in a moment why this is called d. Okay, if I forget to explain it, please ask me. Okay. The d binom function is going to tell you the probability of any of the possible outcomes that you're interested in. So if I say D binom, oh, let's do it. Let's just do it. Okay. Let me see. Right. So first of all, I want you to remember that you can always look up when you're not sure about what the function is doing. You can always type question mark and then the name of the function, and it tells you what that function does, right? It tells you the D binom function's behavior is shown here. The main parameters are shown here. So what I can do is I can compute the probability of getting 5 heads or 5 successes in an experiment of size 10 when the true probability of success is 0.5. 0.5. Okay? So that's how I can calculate the probability of getting 5 heads. I can also calculate the probability of getting 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, and 5 heads, all in one shot by just putting a vector in here, right? Remember what 0 to 5 does? Let me just redo that, sorry. 0 to 5, what does that do? It prints out these numbers, right? So if I type 0 to 5 here, I should get all the probabilities that I want. Okay, so that's something that we can do with this function. I hope I didn't get disconnected again. No, that's good, right? So what I'm doing here is I'm calculating the probability of a particular outcome. Okay, so K successes. So I'm going to call this probability Y equal to some value. I don't know, let's just say K, right? K can be something from 0 to 10 in this case, okay? The other thing I can ask is the following. There's another question I can ask, which is what is the probability of observing 5 or less than 5 successes? This is called the cumulative probability. Right? And you can see how I would do this calculation, right? So graphically, what would I do? I would calculate each of these numbers. Each of the values for 0, for 1, for 2, for 3, for 4, for 5, and add it all up, right? That's how I would get the cumulative probability. And so in this function, I can do that right away by simply typing sum up these numbers. If I just say sum up these numbers, I get the cumulative probability, right? Now in R, there is a built-in function called P binom, P for probability, which tells you the cumulative probability of 5 or less than 5 or whatever number you want. Okay, so this is how the function will work. P binom, right? If I type 5, it puts 5 as the upper bound, and then size will have to be specified, right? Sorry, there's a comma missing, and probability has to be specified. Oh gosh, right? So you can see that the two numbers are exactly the same. So there are two different ways to calculate the cumulative probability. One is by using the D binom function, and the other is by using the P binom function. The P binom function is called the cumulative distribution function, or the CDF. Okay, so it's got a name. This is called the cumulative distribution function right, or CDF. So it's a function of f, right? I can give any number between 0 and 10, and it will tell me the probability of having that value or something less than that, all right? That's why it's a function. And so we will often write that cumulative distribution function like this. We will say capital F, okay? And then K is the same thing as saying, what's the probability of observing some value like K or something less than that? Okay, this is just a notational convention in statistics. The cumulative distribution function is written with a capital F, and then the value that you give to the function is written in small letters. Okay, are we clear on this? So there are two things we have done so far, right? We've figured out the probability of a particular outcome using the D binom function, and we've calculated the cumulative probability of 5 or less successes using the P binom function and the D binom function.
Can I ask something?
Yes, please.
Yeah, I was like a bit confused now with the fact that we are calculating the probability, but the probability is also in the function. So I know that the one in the function is the true probability and the other one is the estimate probability. But can you rephrase what's the difference between those two? How do we know the true probability, for example?
Oh, in this particular case, we know the true probability because we are playing God right now, right? We are simulating data. We are not simulating data right now, but we are actually working in a situation where we are pretending that we know what the true theta is. We are not using the estimate from the data at all here.
Okay, so in
We are
other
ignoring the
situations, you
estimate
might
from the
not,
data.
sorry, in
What
other
was that?
situations, you
Sorry.
might not know the true probability.
Yes, the situation where we don't know what's going on, that situation is yet to be encountered. Right now, what I'm showing you is that if you know the true value of theta,
Mm-hmm.
you can calculate the probability of seeing 0 to 10 heads.
Okay.
So
Yeah.
right now we are studying a situation that is the goal here right now is to understand the properties of a binomial distribution and what questions we can ask of it, having decided on a particular theta. Now you can imagine what I'm going to do next, right? Right? Instead of having the true value of theta, I could plug in a value that I get from an estimate.
Yeah.
That's a
Okay.
possibility. But that's not what the goal is right now. The goal is right now to understand what questions you can ask from a probability mass function. You can ask the question, what is the probability of a particular outcome given some theta? What is the cumulative probability of seeing k or less than k elements, right? And now I'm going to tell you the third thing that you can ask from a probability mass function. Okay, so the third thing you can ask from a probability mass function is, okay, so let me just switch back to my, the third thing we can ask is, so again, let me just draw my picture again. So I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? And I've got this is my probability mass function. I hope it's correct. But basically, I can also ask a question, what is the quantile? So these things are also called quantiles. Okay? What is the quantile such that the probability is the sum of these values here? I can ask the opposite question that I had just posed. The question I had posed earlier was, what is the probability of getting, earlier I had 5 or less than 5, right? Probability of getting 5 or less than 5. So this will be some probability, right? Which I'll call prob, okay? I can now ask the opposite question, which is, what is the quantile? What is this quantile such that the probability is, let's say, 0.34? This is called the inverse. This question can be answered with the inverse CDF function. The inverse CDF function is literally the opposite of the CDF function. The CDF function takes in as input a quantile and gives you a probability. If you flip the axes, turn the x-axis to the y-axis, you get the inverse CDF function. What you do is you plug in the probability, it gives you the quantile. Okay, so let me show you a picture to make this idea solid in your mind. So where's my little CDF function? It should be there somewhere. I've got a picture somewhere of this. I don't know where it is. Yeah, here. This is nice, right? So take a look at this CDF function. On the x-axis are the quantiles, okay? And on the y-axis are the probability of k or less successes. And you can see that it's going up to 1 here, right? The probability of 10 or less successes has to be 1 because that's all the possible outcomes, right? So that's why this cumulative distribution functions have this, this S shape. It's a very typical shape because they're going up to 1 slowly, right? All right. The inverse of this function will simply flip the x and y axes. Let me just flip it, okay? If I could just rotate this, I don't know how to rotate this on Windows, but if I could, I would have this on the x-axis and this on the y-axis. So if I give in a quantile, I would get the probability. That's the inverse CDF. And there's a function in R called Q binom, Q for quantile, right? Which gives you the probability for a particular quantile, okay? So the upshot of all this is that the three important functions that we have just learned, right, are D binom, P binom, and Q binom. Okay, are we good? So these three important functions allow you to ask specific questions about binomial distributions. Now there's a fourth function, which is of great practical relevance to us in this course, and that is the R binom function. Yeah, I've already used it in front of you. This R stands for random, right? Random. Q stands for quantile, and P stands for probability, right? This is the CDF. This is the inverse, sorry, this is supposed to be inverse CDF, and this is just a random generating function. I've not explained what D is yet, but I'll do that later, right? Okay, so what the R binom function will do is that it will allow you to generate random data. And why do we need to be able to do that? We will do that to understand the properties of our experiment design. When we design an experiment with 0-1 responses, like question accuracies or something like that, right? Question response accuracies, we are going to simulate repeated samples of our experiment. Why? Because that will help us understand the properties of that experiment under repeated sampling. Because the whole logic of the frequentist paradigm depends on the properties of repeated sampling. And we can just simulate that world, okay? So this is a unique tool for us to actually understand our design. When I actually run experiments, when I'm actually doing real life research, what I typically do is I will simulate the entire outcome in advance based on my theoretical predictions. And I can do that as many times, 1,000 times if I want to. That helps me understand the properties of that design before I've wasted a single subject on that problem, okay? This is a very, very important tool. This is not taught normally. I will teach it in the second part of this course. We won't get to it in this course, but in the summer semester, I will teach this part, and it's a very, very critical tool. It will give you so much power for understanding your experiments that you won't be ever able to work without simulating, because it doesn't make any sense. You will realize that, right? All right. So these are the four big functions that we're going to need. And I already showed you how this R binom function works, but let me just quickly demonstrate it one more time, right? So one R binom can be used in one of two ways, okay? So I could say, by the way, in RStudio, I always forget what the function names are. If you hit tab, It will tell you what the function, parameters are. So there's n, size, and probability. I have to specify these things. So if I set n to 10 and size to 1, right, and probability to 0.5, what it will do is it will simulate data for me in zeros and ones. Okay, so what it's doing is that it's showing me the result of each coin toss in the 10 coin tosses. All right. So this will keep changing, of course, right? If I want to know the number of heads, how can I do that with this outcome? How do I do that? What do I have to do to count the number of heads in each possible outcome? Think about it. I'll go get some water in the meantime. All right. What do I do? Any ideas? Are you guys still there?
You could take the sum of the successes. That should get you there.
Exactly. I just do sum. I just wrap this entire thing around sum, and it just tells me the total number of heads I'm getting, right? I could do this a different way. The different way would be, instead of writing this command here, okay, I could set n equal to 1 and size equal to 10. When I do that, it prints out the number of successes for me. So formally, what's going on is that the first command is actually showing me the result of 10 separate trials, each with size 1. That kind of trial with size 1 is called a Bernoulli trial. It's called a Bernoulli trial. Okay? Bernoulli was a famous mathematician. When I set size equal to 10, I'm doing a binomial experiment. So there's a distinction. If a size is 1, it's a Bernoulli trial. If size is more than 1, then it's a binomial. Okay, but it's basically the same function. You can see that I'm using the binomial function, right? So it's the same. All right, this is all discussed in the lecture notes. When you read it, you will get a revision on this, right? So it's just an important technical detail. But what I want to show you is how I can now produce random data, right, from this function. Oops, I don't want to lose my signal. Okay, good. All right. So let's get back to my, so what we've done so far is we've looked at the binomial distribution, and we have learned these 4 functions from the binomial distribution. So because we haven't reached the end of this chapter and I'm reaching the end of this lecture now, I'm not going to ask you to do the homework. So I'll give you 2 weeks to do the homework. You don't have to do it right now. I will change it just now as soon as I finish. What I want you to do in this week is to read this chapter carefully and prepare for what's coming up in the next week. I will talk about the continuous example. Okay, so right now I'm using the discrete example of the binomial. The next example I will discuss is the normal distribution, which is a continuous case. And then I will discuss bivariate and multivariate distributions. So in preparation for next week, you should read the chapter carefully. I also have a video recording of this material. I will put it up so you can look at it. It's a different version of this presentation. If you want to look at it, it's from 1 year ago or something. So that's also available. And then once you're done, you should attempt the homework exercises. So you can wait until I've finished talking about it before you do the homework, okay? So that you're clear on everything. Okay, so I still have some 7 minutes to go. So I want to stop now and give you a chance to ask me some questions if you have any.
Sorry, I want to ask, I'm just still a bit confused about the difference between D binom and P binom, just like the difference between the two.
Yeah, that's a good thing to be confused about because they're very closely related. The distinction is the following, right? So if I ask with D binom, if I ask what's the probability of getting 5 heads, exactly 5 heads? Okay, no more, no less. No more, no less, right? And the experiment size is 10. The probability is, I've just decided that the probability is 0.5 because I'm tossing a coin, okay? I'm assuming that it's 0.5. This tells me the probability of exactly 5, getting exactly 5 heads. If I change this D binom to P binom, it's answering a different question. The different question is, what is the probability of observing 5 or less heads? 0 heads, 1 head, 2 heads, 3 heads, 4 heads, and 5 heads. Right? So I have to sum up those 5 probabilities, right? Or 6 probabilities, sorry. Yes? Because there are 6 distinct events, mutually exclusive, right? Therefore, I use the sum rule and I compute that cumulative probability. And that's this number here.
Thank you.
Okay, now let me ask you a test question, all right? So suppose I compute, can I do this? Let me test your understanding now, okay? If I run this command, what should it give me?
The D binom of 5. So what you run before.
Who said that? Elisa. Yeah. It's not fair. I mean, she knows too much. Elisa knows too much. Okay. Let's see what happens. Look at this number here. This number is exactly the same as the D binom here. How did I get that? What happened here? What is this command doing?
I think you exclude the p binom of 0 to 4.
Very good. Yeah. So what we are doing is we're calculating the cumulative probability from 0 to 4, subtracting that from the cumulative probability of 0 to 5. And what is that giving us? The probability of 5 successes, which is exactly what D binom does. So what I'm showing you is that the P binom, D binom functions, they're all two sides of the same coin. They're actually mathematically very deeply related. This you will see later on. You can just go from one to the other through one transformation. Okay. Any other questions? Still have 3 minutes. Okay, so if not, then I'm going to stop recording. First, I have to stop sharing, I think. Actually, I can't figure out how to do that. Let me see. What am I doing wrong here? Ah, here. Wait, sorry. Okay.